Welcome to another edition of Hariba Raman Academy. This installment is titled Depth Profiling of Multilayer Polymer Films by Confocal Raman Spectroscopy. Let's begin by describing the sample that I prepared and these spectra and the depth profile that you're seeing associated with it. This is essentially a homemade sample. I took some polymer packing material that came with a monitor that I purchased. There was a large sheet of very thick polyethylene terephthalate, and then around the edge of the monitor there were some very thin films of polyethylene with some adhesive on them. Well, I got the idea that maybe I could make just artificially a multi-layer film by pressing the polyethylene on top of the polyethylene terephthalate and just testing how effective one could confocally profile the depth in moving the focal plane down through the polyethylene through this very weak interface into the polyethylene terephthalate. And so that's what we'll look at today, and I'll show you not the actual data acquisition, but then how to treat the data afterward when you have obtained this depth profiling. So what you're looking at now are data and a data set, this one called 2film_2, which was obtained with the laser beam incident upon this two-layer film and parallel to the normal of this two-layer film. And then what I did was to just begin with the beam focused approximately at the surface, which would be at the polyethylene, and that would be approximately the 0 position, and then move the laser beam, or move the stage up, which is to say move the focal plane of the microscope objective and the laser beam down through the two-layer sample. Now we can click on this letter I here for information about the experiment as it took place, and this is where all the metadata are stored, so that you can see that what I used was the Explorer, and I basically I used a total of 9-second integration time. I was being kind of slow. I wanted to make sure that I got as good a signal to noise as I can with the slit being at its most narrow position, 100 micrometers, and the hole at its smallest position for the Explorer, 100 micrometers, and a total of 3 seconds for 3 accumulations, which is to say a total of 9-second integration time, with the spectrometer set at 1500 wave numbers. This is our actual laser wavelength, and all the other settings are indicated here as far as the detector size, the CCD, and the original Z position of the stage, 0. Okay, so there's all the information about our experiment. And now what you see in this screen is essentially a collection of all of the spectra overlaid. And notice I have 3 brackets here: a red, blue in the solid line, blue in the dotted line, and if we want to change that, make the blue active, we can now just click on the blue arrow here, or if we want to make the green arrow active, we can click on the green arrow. And what I've done here is I've bracketed the blue and the green around polyethylene Raman bands, and I'm moving the red bracket essentially around the carbonyl band of the polyethylene terephthalate. And then as I did that, you can see that the response of this profile for the counts was changing as I moved that bracket. And what do we mean by a response here? Well, and I'm just going to expand this. These are basically the integrated intensities of these peaks between the green, the blue, and the red cursors. And so what we see is that if we if we segregate off the peak areas associated with the polyethylene, then the polyethylene is strongest from approximately 2.5 once the beam is fully into the film, to about, let me say, around 35 micrometers or so. All right, so this film is probably approximately probably 30 micrometers. All right, and then once the focal plane starts moving down through the polyethylene, then we start seeing the onset of the peaks associated with the polyethylene terephthalate. And so if you wanted to, you could generate a depth profile just from tracking the peaks associated with the different chemical compositions. And also, if you wanted to identify the particular spectra at any acquired at any location in these depths, you could do so by moving the cursor in this profile or map page, and then you see over here is the spectrum associated with that particular position. Okay, so now we're at a position of basically 5 micrometers, and that's indicated down here. It says 5, right? So that's at 5 micrometers, and this is the spectrum acquired at 5 micrometers. And as we move through this, you're going to want to watch these bands right here as we move through the polyethylene and move deeper and deeper now towards the bottom of the polyethylene. Now you begin to see the polyethylene terephthalate becoming absolutely dominant in the spectrum, and the polyethylene essentially vanishes. And that's because, as you can tell from the signal to noise, the polyethylene terephthalate is a much stronger Raman scatterer than is the polyethylene. Now, we've looked at this depth profiling as a mean, or by peak area, by selectively picking off peaks that are associated with this material. But we can also get a profile by modeling as well. And how do we do that? Well, I'm going to click this set of data back on, and now I'm going to open up 2 spectra, my reference spectra acquired of these films from which I made the multilayer, and I acquired these spectra separately. All right, so here you see the blue spectrum is polyethylene, and the green spectrum is polyethylene terephthalate. These are my reference spectra. So what I'd like to do then is to load these reference spectra for modeling in order to then use not just one particular peak, but the entire spectra to then model my depth profile. And I'll do that by clicking on this button here, which is just to the left of the stop sign. And because I had just previously highlighted this spectrum, which said PET1, and I had both of these spectra loaded, I will now click Get All. And when it does that, it has basically extracted those 2 spectra as my model spectra. And now what you can see is that in my depth profile that's generated from the modeling, now we have a depth profile that is not just from one peak, but from a depth profile generated from known reference spectra. And here we see now a much sharper interface than we saw with the one peak. And I have these plotted normalized so that if we take into account the fact that the beam was perhaps not in focus at right at the very top, and it reached its maximum here at about 2.5 micrometers, it seems reasonable then that the thickness, the actual thickness of this polymer film, is probably going to be I would say approximately in the 35 micrometer regime. Now, I said thickness, but remember, this accounts for just the stage travel. And so what we'd really have to do is get the refractive index of the polyethylene and the polyethylene terephthalate in order to convert this axis into a true depth axis for the polymer film. But if you essentially wanted to get a general map or profiling that was approximately close to the true depths, and you wanted to identify films that were buried or underneath, then with a limited degree of accuracy, then the stage motion itself can work quite well. Well, that's our edition for today of the Horiba's Raman Academy. So you can see that these are not scripted, and I do my best to just speak extemporaneously. If you have any questions about the work that's done here, or have any requests for further videos that might help explain our software, our data analysis procedures, or even experiments that may be of interest to you with our Raman instrumentation, please contact us at Horiba Scientific. Thank you.